Hey everyone, today we're diving into a really fundamental shift in how we create new technology. We're talking about moving out of the physical lab and into a virtual world where things like AI and so called digital twins are just completely changing the game and accelerating innovation. Let's get right into it. But first, I want you to think about this for a second. What if you could test a million bad ideas in a single afternoon and not spend a single penny on materials or building a prototype? I know, it sounds a little like science fiction, right? But this question is really at the heart of the whole revolution we're about to unpack. To really get why this change is so urgent, we need to talk about the huge pressures facing the semiconductor industry. It's kind of created what you could call an innovation traffic jam. I mean, the world's appetite for new, more powerful chips is just exploding. And this isn't just about making your smartphone a little bit faster. This is being driven by massive AI models running in the cloud, by advanced packaging that lets us stack chips together. It's coming from everywhere. And the problem, well, it's coming from a few different directions. For one, the manufacturing processes themselves, things like etching and deposition, are now happening at the atomic scale. It's just insanely complex. At the same time, you've got all these different markets, logic, memory, packaging, and they each need their own custom solutions. And through it all, the timeline for innovation has shrunk from years down to months. So the old way of doing R&D, build it and see, is now a massive bottleneck. We just can't solve this by making small tweaks anymore. To really break through this traffic jam, we have to completely change how we do R&D. And really the only solution that can scale is to bring in AI and move the whole process into a brand new dimension. So what is this new dimension? It's the virtual world. And this creates an entirely new way to innovate. We're shifting away from that slow, expensive trial and error method and moving toward rapid prediction and simulation. And the difference is it's night and day. The old way is slow, it's incredibly expensive, and it relies on building physical prototypes and running experiments that can take months. The new way is all about speed and efficiency. Instead of building, you simulate. Instead of guessing, you use predictive models. This is a complete game changer when it comes to time to market. So the main goal, the core objective, is crystal clear. Let's do the bulk of our research and development in a virtual space. This is a world where engineers can explore literally thousands of possibilities, all powered by simulation and advanced analytics, before they ever have to commit to a single, expensive physical experiment. Okay, so how does this virtual world actually work? Well, the magic behind it is a concept called the virtual twin, or as you might have heard it, the digital twin. Let's break down what that really means. So a virtual twin is basically a dynamic, always evolving digital copy of a real piece of equipment, say a semiconductor reactor, and all the incredibly complex physics and chemistry that are happening inside it. This is not just some static 3D model, it's a living simulation that really understands what it's replicating. A great way to think about this is to imagine a flight simulator, but for a multi-billion-dollar semiconductor process. You wouldn't learn to fly a brand new jet by just taking off and risking a crash, right? You'd use a simulator so you could fail 1,000 times for free. This technology brings that exact same powerful idea to making chips. And these models, they're not just static blueprints. They are constantly evolving, always growing in complexity and scale. They start at the tiniest atomic level of a single transistor. Then they scale up to model an entire piece of equipment, and the ultimate goal is to model the entire factory. Now, the real power of this system comes from a super clever two-step process. First, you have what's called a forward model. That's where you give the simulator your recipe, things like gas flow, temperature, and it predicts what the chip will look like at the end. But the real magic is in the inverted model. Here, you give it the target, the customer's exact specs, and the model works backward to figure out the precise recipe you need to make it. So it's not just predicting, it's prescribing solutions. This quote really just gets to the heart of why this is so valuable. The ultimate goal is to find and get rid of all the dead ends, all the paths that are never going to work right at the very beginning of the development cycle. It's just like pruning the dead branches from a tree. By getting rid of experiments that are doomed to fail before you even start them, you save a staggering amount of time, money, and resources. You can focus your best engineers only on the ideas that have a real shot at working. So, we've gone from a single process to a virtual machine, but the ultimate vision is even bigger than that. We're talking about connecting all these individual twins to create a fully virtual factory. The ambition here is to create this huge, interconnected system of digital twins. So imagine connecting the model for deposition to the model for etching, and then linking that to lithography, and so on for every single step in the entire chip-making process. And the power of that is just profound. You're no longer just optimizing one machine by itself. You can simulate and optimize the performance of the entire factory. You can predict how one tiny change in step 1 is going to ripple through and affect the final result in step 20. And you can do all of this before a single physical wafer is ever touched. This means higher yields, faster ramp-up times, and a whole lot less waste. But there's a big challenge to making this vision a reality, and that's the need for industry-wide standardization. For a virtual factory to actually work, all of these incredibly complex models, which are often built by different competing companies, they all have to be able to speak the same language and plug into each other seamlessly. And this leaves us with a really fascinating final question. We're on this path from simulating atoms to reactors to entire factories. So once we've done that, what's next? Simulating the entire global supply chain? It's a massive leap, but it really shows you the almost limitless potential of the virtual lab, and it might just change our very definition of how we create things.